Bismillahirrahmanirrahim. Welcome to Diode and Application Season 2. In the previous episode, we discussed an example that include the ideal diode model in which there is a constant output voltage that does not include the impedance. But in today's episode, we include impedance that is in this case 14 ohm, and we use 1N4744A, that is 15 volt and 1 watt, basically a regulator, and IZ test current is 17 milliampere. First of all, we draw the graph here. This is the IZK point, IZK. This is the IZ test current, and let's say this is the IZ maximum. This is the knee point, and we are getting here VZ constant voltage. In this is the breakdown region of the Zener diode normal operation region. Okay, what we want, first of all, let's focus on the statement of the question. What the question basically demand. First of all, we have to determine the V output at IZK and at IZM. We have to calculate the V output voltage when there is no load. When there is no load, it is the situation that the maximum current will flow through the this diode, and this is the point. And after that, if we calculate further, then our regulation will lost. We should be this is our maximum point. If we should, this is the limitation. We cannot cross the IZM because our regulation will be lost. So maximum point is the IZM. We have to calculate that, as it is mentioned in the question. We have to calculate it, our value at IZM, and determine the output voltage when there is no load connected. That is the situation IZK. So we should be in the limitations, that is the lowest value is the IZK. If we further added the load, the current will maximum flow through this side, and the current is reduced. Even it will go below the IZK knee point, and it will lost once again regulation. So this is the lower peak and this is the maximum peak. So both peaks must be in mind before changing the voltage current. If we do not understand these points and do not come into mind and change our current without irrespective of these points, then definitely there is a problem that our regulation may be lost. Calculating the value of R that should be used. This is the value of R. We want to calculate this value when there is a no load connected. I will also explain when we are going to calculate. This is a C part that is the same as we have already explained in the previous lecture, that determine the minimum value of RL that can be used. This is the value of R. We have to calculate this value of R when the in a situation when the heavy load is connected. Means to say, determine the minimum value of sorry, this is not R, this is R. This is we have to calculate the minimum value of R. Means to say heavy load, how much load we can add in the parallel with this Zener diode. Means to say how minimum value of RL. Minimum the value of RL means that the maximum load we can add. We have to find the value of the resistance in ohms. This is your you have to calculate this third portion by yourself, because we already calculated this type of question in the previous episode. Let's start our first, that is the part A. For IZK, this is a case when we had connected our maximum load, and the maximum current will flow through the across RL. So the minimum current will flow through this through the Zener diode, and at this point we can say that our current through Zener diode is at point IZK. So at IZK, our output through the Zener diode, V output is equals to V Zener, that is 15 volt. We are basically receiving 15 volt. But when we added some load, and we load is heavy, and our current will be definitely reduced towards this side, and this is IZK. Then if our current is reduced, then it is understood that by changing this current from this point, definitely little bit change will occur in the regulation. So it will definitely be subtracted. It's understood it's subtract, because if we are going, current is going downward, by current, if current goes downward, we will definitely move towards the zero side, and or you can say if this is, let's say, 15 volt, it will be definitely subtracted to get when we move towards right side towards the origin of the graph, it is the values are lower. If we add goes below these sides upward towards the at IZM, then our value will be definitely towards the left side, and it's basically the 15 something plus. Okay, first of all, let's calculate for IZK. V output is equal to minus change in the VZ, that is basically VZ minus basically what is the change, that is V is equals to IR. So IZ, R is basically impedance, internal resistance is basically impedance in case of the Zener diode, that is Z. So in subscript basically Zener, so we use the Z in subscript, that is indicate that Zener's impedance. So by substituting the values we see what is the change in the current, that is I Zener impedance test current, and we basically decrease this value. For example, let's say this is 15 ampere current, milliampere current, and we change this towards the IZK, and we are now at 0.10. So it means that how we can calculate this, these points basically change. Here is the 15 minus 10 and this is 5. So we can calculate this in other words by IZK subtract IZ subtracting IZK. So we can write IZ minus IZK and multiplying Z. This is the way how we can find. This ways you got this. I will explain once again. You basically you should keep this trick in mind or formula in mind. Basically that higher value will be always lower value always subtracted from higher value. So 15 milliampere is at point IZK, and it is the higher potential, and IZK is lower. So IZK is subtracted from IZK. So VZ in our case is 15 volt minus 16.75 milliampere. By subtracting these two terms, I'll write direct, and Z is here 14 ohm, that is this, and after calculation that is 14.76 volt V output. Okay, for second case, for when there is no load connected, then the maximum current flow through this, then this is the situation called IZ maximum. So in this case we can say that same is the situation, but V output is equals to VZ plus V delta VZ. Something is added, as I already explained. V output is equals to VZ plus what is the change, that is delta IZ Z. Same situation, V output is equals to VZ plus what is delta IZ. Delta IZ, for example, it's 15 ampere. By increasing to when we reach to this point, it is some let's say 20 milliampere. So how we can calculate, this is the higher value right now. Now we have to subtract 20 minus 15. So we can say 20 is basically higher potential right now. So IZ maximum minus IZ, we can calculate this. So we can write it IZ maximum minus IZ multiplied by ZZ. Here important thing you have to note here, that there is not IZ maximum is not given in the data sheet, as we already explained in the previous episode how to calculate if IZ is maximum is not given. Power dissipation formula. What is power dissipation? Power dissipation is equals to P is equals to IV. If you want to calculate the current from here, I is equals to PD over V. If I want to calculate I current, that is for example IZ maximum, then power dissipation maximum, power dissipation maximum formula is changed to power dissipation maximum divided by V Zener. IZ maximum can be calculated from this formula, 1 watt divided by 15 volt, that is 66.7 milliampere. So substituting this value here, V output is equals to VZ, that is 15 volt plus IZ maximum 66.7 milliampere minus IZ, that is where is shift 17 milliampere, and Z is 14 once again 14 ohm. So V output here is 15.7 volt, that is available in my notes. You can also calculate by yourself. If there is any mistake, you please point out. In the second case, I'm going to pause out by writing a simple, I'm going to draw a simple diagram once again. This is the same diagram. I write it here for clarification, for further clearing the concept. This is the Zener diode, again connected, same, everything is same. Now we want to calculate this value of R. I write it here by mistakenly I write it here because in my notes already calculated, but we want to calculate here. Okay, first 24 volts is coming from the previous here 24 volt power supply, 24 volts, and if there is no load is connected, then maximum current is maximum current will flow through the Zener diode. And in this case, when the maximum current flows, that is this where we calculate the 66.7 milliampere, we already calculated the maximum current flow, and 15.7 volt, in this case the output is 15.7 volt in the already calculated. But when the situation in which the maximum current flows, the protection is necessary. So because we want to protect our Zener diode that it will not burn out, so limiting resistance is necessary. So we want to calculate the limiting resistance, and in this case, you whenever you are basically calculating the limiting resistance, you have to focus on the maximum rating of your circuits. Okay, this is a point. Okay, R is equals to V over I from Ohm's law. In this case, R is equals to V input minus V output. What is this basically? I change V output voltage here is basically 24 voltage is coming, and output is 15.7 volt is 15.7 volt is taken. So by subtracting this, we can also calculate that how much voltage is stayed here. And R is equals to V over I, and I, what is I? I is maximum, that is the maximum current flows through this side, that is IZM. R is equals to this V input, that is 24 volt minus 14.76 volt, minus 15.7 volt divided by 66.7 milliampere, and after calculation 124 ohm will be is the answer. That is the approximately answer, but we can use this value out for the nearest larger standard value. We have always select the standard available is in market is, for example, if 130, you can use 130 ohm is fine. No, there is not an error. Okay, but the third part is up to you. You can calculate. Same is the same procedure. I am going to give you also hint, and in this case, the third part is the determine the minimum value of RL, means to say the maximum load. So RL minimum is V output divided by IL. R is equals to V over I. V output voltage is given already, but you can calculate the IL. This is the question you have to find out IL. So IL can be calculated as IT minus IZK. Okay, next you can have to calculate the I total, and IZK is already available, but this is up to you. You can also write in comment section. Use comment section most of the time for clarification with each other, to communicate with other students, so that other students may also get clear their concepts by using for example, if you solve this question, use your comment section. In comments, you told other students that I calculated this and this is my answer, and other students also calculate, so you can compare your answer with the other students. So this is the way we can calculate. This is a cheap way of providing in the whole discussion we discussed. This is the cheap way of providing the regulation by using Zener diode. You can see that there is a limited basically changing available in the load current. If we added a load, there is current changing, but there is a limited portion available. So for better, we basically combine the Zener diode with the other circuit components, and we made a voltage regulators called voltage regulators. In voltage regulator we use Zener diode and other circuits, and we will discuss voltage regulator later and extra other series, not here, but we will discuss here only diodes. But this is an explanation will be available maybe when you watch this episode later, in maybe after 2 years or 1 year, then maybe voltage regulator series is available on the channel. You can maybe watch on our channel, visit our channel. Okay, this is the V input and this is V output. Three terminal voltage regulators are basically three terminals. This is input and this is output, and this terminal is basically ground. So this is not a discussion right now. This is not a topic right now for discussion. I want to tell you that from the next episode we are going to discuss the Zener's limiter. Zener limiter, we will discuss how we can limit the voltage, AC voltage, by using the Zener limiter. So this is the next topic we will discuss in the next episodes. So see you next time. Watch, learn, grow.